Hello and welcome to an introduction to Kubernetes. My name is Joseph Irving. I'm a senior software engineer at RVU. I lead the cloud infrastructure team at RVU, which are responsible for running the Kubernetes clusters, among other things. And I'll be taking you through this session today. Now, to give an overview of the session, we're going to quickly go over the history of kind of how things like Kubernetes came about. We'll talk about what actually is Kubernetes, and then the meat of this thing will be a workshop in which we will take a sample application and deploy that onto a Kubernetes cluster. So before we start, I thought I'd mention a few of these tools. These will all be used throughout the workshop section. If you want to follow along, please install all of these. Minikube and kubectl will be essential for the Kubernetes aspects, and you'll need Docker for building some containers, and Git to clone the repository down, which we'll be using as the basis for what we will be doing. So please pause the screen if you like, and go install those things if you don't have them already. Oh, so let's go back in time a little bit to the kind of classic world of server architecture, where a server would generally be a single-use thing, perhaps, where it will run an application of some sort. And the server and the application were generally quite tightly coupled. So, for example, if you had a Java application, your server would need to have the JVM installed, and it would have to match the version of the app you're running, and all these kind of things, which often meant you couldn't have multiple different things running on one server because of tight coupling between dependencies running on the host. So often servers were single purpose or only had a few purposes and had their life cycle often tightly coupled to the applications that were running on them. Now, along came containerization, and this suddenly allowed people to run multiple applications on one single server, regardless of what was installed on that server. With containers, they have all their dependencies packaged within the container itself, not on the actual host machine. So as long as this host could run some kind of container runtime, in this diagram it's that Docker is used, you could run whatever you like on it without needing to worry about this intercoupling between your infrastructure and your application. Now, this could be scaled horizontally, perhaps, with people running multiple of these servers with multiple copies of your application, doing things like load balancing between them. And you could also scale relatively vertically on a machine, where you could keep running multiple copies of the same app, or maybe different applications. You could have whatever you wanted running on this server. Now, while this was good in that we no longer had these servers that were tightly coupled to our applications, this in itself brought upon its own challenges. And every company that adopted this would soon end up developing their own mechanisms to solve these problems. So some of the problems that you might encounter are things like scheduling, which is how do I know where my containers should be running? If I have multiple servers that could all possibly run it, where does my container run? How do I do a rollout? So how do I take down my old containers, spin up new containers of a new version of the app, let's say? How do I health check that my app is running successfully and therefore should be serving traffic? And also problems such as how do I persist storage between my containers and some other storage device, perhaps? And how does this work across multiple different nodes? So a lot of companies came up with their own solutions to this, often could be quite bespoke in-house solutions, which while worked were perhaps quite complicated, hard to maintain, and required a lot of in-depth knowledge at the company itself. So in the midst of all this kind of container revolution, we had Kubernetes. This came out of Google, who themselves had their own in-house container scheduling system known as Borg. Now, Borg was not intended for the wider world to use. It was very much bespoke to have Google do things. So they didn't see the need to more widespread share this because it wouldn't have been useful. So instead, they developed Kubernetes, taking a lot of the lessons learned from Borg and turning it into a much more generally applicable piece of software that hopefully everyone could use. It's an open source repo. Anyone can contribute to it. At this point, it has contributors from all over the world, from various different companies, big companies like Red Hat, IBM, Google, Amazon, etc., as well as smaller companies such as ourselves at RVU. So what is Kubernetes? At its core, it is just a way to schedule your containerized workloads. It handles a lot of those things we had in the last slide for you. And it has a declarative language, which is all generally in YAML, which can be used to define all these things, which is nice because we now have a common language which we can share between clouds, between companies. It's a common way of talking about applications and their other bits of infrastructure that surround them. Now, Kubernetes runs in a cluster. The cluster consists of masters and nodes. The master is responsible for making all the decisions in a cluster, such as what containers should get scheduled where, as well as having the API server, which you can interact with to query information about the cluster, as well as this is what the nodes also query. So the nodes just query the master for information about what containers they should be running and then run them. With something called the kubelet, which is just a daemon process that runs on all the nodes and is responsible for ensuring containers are run where they should be. So yeah, the master decides where containers go, and then they get put on your nodes for you. Now in Kubernetes, though, this is more commonly referred to as a pod, which is similar to a container, but not quite. What is a pod? A pod is just a abstraction around a group of one or more containers. So a pod can have 5, 10, whatever containers in it. It commonly just has one container in it, but it is a wrapper effectively for defining containers. Any containers in that pod can share the networking or file systems between one another very easily, so they are tightly coupled. Their life cycles are intertwined. When the pod is deleted, all the containers in the pod will go away, and vice versa. And the pod is just kind of a general wrapper in which we can define other kind of lifecycle abstractions which are a bit higher level than the container level. So yeah, a pod is effectively your building block in Kubernetes. Everything tends to relate to pods at the end of the day. Now, just taking one step back, some of you might be questioning why is a container? And the way I like to think about a container is it's just an application packaged up with all of its dependencies. So it is, if it's a Java app, it is in a little container with the JVM, with any other utilities that this application may require to run. And that is all it should be. It's a little unit of application. And this can be ran anywhere where container runtime is present. You'll often hear we use the word Docker and container runtime interchangeably. This is because Docker is by far the most popular, most well-known container runtime. There are others, and they'll work in basically the same way. But this allows you to take an application that would need a load of dependencies, but just package it up and then ship it anywhere, regardless of what the underlying host has installed on it. And you can have multiple containers all running on one server without them interacting with one another. They're isolated, that being file systems, networking, etc. There's certain levels of isolation between containers, which makes it easy to have them all running on the same host without kind of clashing with one another. So yeah, so that is just a kind of brief overview of what Kubernetes and containers are and where it kind of stemmed from. Now, hopefully a lot of this will start to make more sense as we actually do some practical applications of all this knowledge. And that's what brings us on to the workshop section. Now, as we move into the practical section of this, if you want to follow along at home, please go to this link, which is github.com/uswitch/Kubernetes training. This is a repository I've made which contains a number of examples, templates, the actual application that we're going to be working on, as well as some instructions for how to do some of this stuff yourself. So if you want to follow along, please just clone this repo down to your local machine. If you don't want to, that is fine. I will be showing everything on the screen myself, but this is just if you want the extra experience of kind of doing it for yourself, you can use this repo as a starting off point. So let's just have a quick look inside the repository. So I've just got it open in my IDE here, and I will show this main.go, which is the main repository that we're going to be working on. It's written in Go. Do not worry if you're not super familiar with Go, as it's not that important what we're going to be doing going forward. I will just point out some key things to note about this application. One of which is when it starts, it prints a little message saying starting up, just out to the standard out. And then it creates a web server, and this server is listening on port 8080. And when we hit the server, it has a handler / which will just return us the bytes that say hello there. And that is basically all this application is doing at the moment. It is just running a web server on port 8080, and it will return a simple response. Now, if you have Go installed, you can do go run main.go, and you should see those things happen. So it's starting up. If I go back to my web browser and go to localhost 8080, I get a hello there response. So there we go. That's the app in action. Now, that's all very well, but we need to turn this into a container. So to do that, we're going to be using Docker, which hopefully you installed earlier. Which Docker has a CLI tool, which works kind of how you expect. You use Docker and then a verb of some sort. So we'll be using that going forward. So bear that in mind. So for example, Docker images lists all your images on your workstation. Now, before we actually start building something, we need to create a Docker file. Now, if you go into the templates directory in this repository, you'll find there is a file called Docker file, which we can start building upon. Now, the first thing you'll see in this is we have from Golang 1.14. This is the base image that all the rest of our commands in the Docker file will start running upon. And always think of a Docker file as like a recipe almost, or a set of instructions on which we will use to create our image to run our application. So first we have from Golang 1.14, that's just specifying what we're going to run from. Then I will put in the work directory of /. This is just where we'll be executing commands, and don't need to worry too much about this. And then we will copy in our main.go. So that's our actual binary that we have specified here, our actual Go application. And then I will copy in this command because it's quite long, but we're going to run a command. So run tells Docker to actually execute this command. So it's going to execute a command which is doing a go build command. This will actually build an application and output it as app. And then the last thing you need is an entry point. Now what this is it's the command that Docker will run when it tries to run this container, which in our case is just /app. So there we go. So from Golang 1.14 in the /root directory, I want you to copy in my Go binary. I want you then to just compile that into an actual binary, and then I want the entry point to be that binary I just compiled. Right? So I'm copying my Go file, I'm compiling it, and then I'm going to use that as my run point. So that's our kind of recipe for our Docker file. Now, to build this application, we're going to go back to the terminal and we're going to use our Docker tool. So the command is docker build, and we can do -f to tell it where to build from. So we're going to tell it to use that Docker file we defined in templates Docker file. Then we give it a title, which we can do as my app, and we can do dot just to execute where we are, and that should be it. And now it starts building. So the first thing you'll see it doing is it will start downloading that Golang image if you don't have it present on your machine. This might take a little while depending on your internet speed. Luckily mine is relatively fast, so this won't take too long. Once it's pulled that down, it will start executing the actual steps. So give it a second, here it goes, it's extracting the layers. Now you'll start to see it doing each step in the things. You can see it doing the work there, you can see it doing the copy, you can see it doing now it's doing the compile command, and there we go. So once that's finished, you can run the command docker images, and you'll see all the images on your machine. So you should see probably 2 if you've just installed Docker, which is Golang, which was that base image we used. You can see it was last updated 13 hours ago. And you can also see my app, which we just created 8 seconds ago, and it's roughly 826 megabytes. Now, if we want to use this, we can use the docker run command. You can do docker run -ti, and then we give the container some kind of name. So serve doesn't really matter. And then we use the image of my app. Oops, sorry, I did it the wrong way around. There we go. So that should run my app. There we go. Which you can see it's logged starting up. So which is what our app logs. So that is just running our application. Now, at this point, we can't actually access the web server or anything like we could earlier. For example, if we go back to localhost 8080, nothing happens. And this was because Docker runs on a completely isolated network by default. So if we want to actually be able to run this and access it, we'll need to do some port binding. And we do this with the -p flag, where we can define ports and bind them to our local ports. So I'm just going to bind 8080 to 8080. So this means the port of 8080 in the container will be bound to the port of 8080 on my local machine. So we do it again. And now, if we go to localhost 8080, I get hello there. So now I've actually connected to the machine. This is an important concept to realize, is the idea that by default the ports in Docker aren't necessarily exposed, and you have to kind of manually say, I want to be able to access this port because the network is separate from the rest of your machine. There we go. So we created a container, and then we can run that, and we can run it anywhere. And regardless of what machine you are running on, you should be able to compile and run this, because it all runs in the container. It's not running on your machine. Now, that is good, but you may have noticed something, which was our Docker image is actually quite big. It's currently around 826 megabytes, which is fairly chunky for something that's not really doing much. So what we can do is a fun little trick in Docker, which is to use a from scratch container. Now this doesn't work for all languages, but it does work for Golang, because Golang just runs binaries and doesn't really require any other dependencies. So that's just worth bearing in mind. But from Golang, we can use a from scratch container and run it in that instead. And so what we do with this first step is we can define this as a build env. And then what we're going to do in our second step is we're going to copy from that build env, that's just referring to that, my app. So I want to copy my app that I compiled into my build env and put it into this from scratch container. And then I just want that same entry point. So I'm going to move the entry point into my from scratch bit. So what I'm doing here is I'm doing all the compilation of my Go app in this Golang image, but actually my final image will be this from scratch container, which just has my app and nothing else in it. So if we do that docker build command again, which is templates dockerfile -t my app. It's the same thing. It should be pretty speedy because we've already done it. And then if we check our images, nice. I have my app image again, but this time it's only 7.42 megabytes large, which is much, much more reasonable for such a tiny app, and will allow us to get super fast speeds of pulling and whatnot in a production setting. So that's a nice little tip for making super small applications when using Docker. So we have made a container now. That's great. We made a Docker file, which was the recipe for our container, and we have compiled that into an image that can be used elsewhere. So the next part that we'll move on now is to actually turn this into a pod. So the first thing to do when we're creating a pod is to define a pod manifest. Now this is one of the first of many Kubernetes manifests we're going to be creating as part of this workshop. They all kind of look the same, and you'll get more used to them as we go along. But this is the basic for a pod. So all Kubernetes manifests have a few things in common. They always have a kind, so in which case we have a kind of pod. The API version, which is just used for versioning these resources behind the scene. We have some metadata, such as the name of the pod, some additional labels we can apply to it, and then the spec, which is a common thing, where we will define the containers that will be running in our pod. So if we go back into our repository in the templates file, you'll find we have a pod.yaml. So I've just created a basic outline of what a pod looks like, so we can fill this in as we so desire. So we can create a pod called my pod. Give me a name. We can give it a label, such as the label name is my app. Now inside the spec we have containers, so for each container it can have a name just as a unique identifier. This is completely arbitrary. We can call it server if it's a web server, and the important bit is we give it our image that we defined earlier, which was my app, and the tag is latest. And that is it. That is a basic pod definition. Now we're going to actually create this. So before we do that, we need to actually start our Kubernetes cluster. And the way we do that is if you run the command make minikube, that should start spinning up a Kubernetes cluster on your machine. This may take a little while as it has to pull some things down. Mine's already ready, hence it being so quick. But once you've done that, you should have a Kubernetes cluster ready to go. Now there's also this important command down here that you need to run in your terminal. So what this does is it will set the Docker daemon on your machine to actually be the Docker daemon on the Minikube machine. Now, basically what we're doing here is we're allowing the Docker images that we build in this terminal to go to the virtual machine that's running Minikube, because otherwise they wouldn't be connected. This is just so that we can easily pass our Docker container to the Minikube cluster, because we're not going to like host our Docker container in an online registry or anything for this demo. So that's all that's doing. If you run a Docker images, after doing that, you should see a load of extra images have appeared. And the reason for this is because we're now actually getting our images from the Minikube machine, not our own local machine. So that's that. So to actually interact with the cluster and like create this pod, we're going to have to use the Kubernetes CLI tool, which is kubectl. There are many arguments on how to pronounce that, but I pronounce it kubectl. Now, it's your go-to tool for doing anything Kubernetes related. It has a fairly easy to learn kind of pattern for how you do things, where it's always kubectl with a verb, a resource type, and a resource name. And we will explain the various commands as we go through the workshop, because there's hundreds of possible combinations, but as we get to them, I'll try and explain what I'm doing. So, for example, I can do a kubectl get pods, and this will return any pods in the cluster. But as you can see, there's no pods in the current namespace we're in, and that's because we haven't created any. So that's to be expected. So before we create a pod, one thing we can do is if you run make docker, this will just rebuild that Docker image we did earlier, but this time on the Minikube machine. If you do Docker images, you can just verify that we do have that image. There is my latest on the actual machine, because we're on a different Docker daemon now, so we just need to make sure that's there. Make Docker is just a handy, quick way to regenerate the Docker image if you need to, without typing out all the Docker commands. So once we've ensured that image is there, we can do a kubectl apply-f templates pod.yaml. So what we're doing here is we're applying onto the Kubernetes cluster from a template, which is that pod YAML, and the -f just means from file. Hit return, and we'll see my pod was created. So if we do kubectl get pods now, we can see I have one pod running called my pod. Now we can do a few extra things with this pod. For example, we can do logs, kubectl logs, and this will give us the output of the logs from the pod. So you can see it says starting up, which if we go back to the application code, that's what we have here. So that's good to see, it's doing what we expect. Now another handy command is port forward. So we can port forward to the pod. And what this means is we're going to bind the ports from the pod to our local machine. Similar to when we did that docker run command with a -p, we can do a similar thing to a Kubernetes pod. So we'll be port forwarding and we'll be binding 8080 to our local machine. And now if you go into a web browser, there we go, we're still getting hello there, as we're getting a response from the server. Nice. So there we go, we have created a pod and it is running our image and it is inside of the Kubernetes cluster. So now that we've got a pod, we can start adding some additional resources to it. And the next thing we're going to do is add something known as a service. Now, a service is a concept in Kubernetes which allows you to effectively create a network endpoint to sit in front of pods. And the service can be mapped to many pods behind it. So you can have, 5, 6, however many pods behind one service. And the service kind of acts like a networking address or a load balancer for your application. So requests can hit the service instead of the pod and get routed to a pod that will be able to respond to your request. So another pod, for example, can hit the service address and go to one of your pods. Pods in Kubernetes are considered ephemeral. They can come and go, their IPs can change, nothing is considered static. But a service is static. It's like a static point at which you can always address to get routed to one of the pods. So to create this, we, in a very similar fashion to how we create a pod, will create a service manifest. And you'll notice a number of similarities between this and the pod. We have the API version again, we have the kind, this time it's a service, we also have the metadata again, this time the name, and we have a spec. The spec's a bit different for this example. It has a type, there are different types of service that you can use from. We're going to use a load balancer type in this example, but there are others. We're going to have a selector. This is important. So the selector is how the service knows what pods it should map to. So the selector in the service has to match the label we put on our pod earlier. I'll come back to that. And then we also have a port. So we can bind ports from the pod to the service. So for example, this service can listen on port 80, but it will be actually targeting port 8080 on our containers. This is a quite common pattern because low numbered ports, which is port 80, which is commonly used for HTTP, and port 443, which is commonly used for HTTPS, are privileged ports, which you need to often be running as root to actually expose your application on. So it's far more common for your application to run on a high numbered port, such as 8080, and then it's your service that can actually be on the low numbered port, because that doesn't require any extra privileges. So let's go back to the repository. If we go into the templates, we have the service.yaml, and we can fill this out similar to how we filled out the pod YAML. So we can call this my app, if you like, just keeping the thing going there, is my app. And so this is the important bit though, it's a selector. So this app has to match what we had on our pod. So on our pod, we gave it a label of app, my app. So these have to match. So in the service, we need to make sure the selector is on app, my app. And that will make sure it binds to our pods. And then, yeah, we want to bind on port 80, and we'll do 8080. So that's telling us to hit the 8080 port on our containers, but be exposed on port 80. There we go. So that gives us a service. So very similarly to how we create a pod, we will do a kubectl apply, but this time we will apply the service.yaml instead of the pod.yaml. and this will create a service. So similar to how you can get pods, you can get service. You can do that by doing get service, and you'll see there's two services. We've already got this one called Kubernetes, but there's also one called my app. Now, you can also do SVC as a nice little shorthand, by the way. This is quite commonly used. Yeah, we have a service called my app. Now, what we can do here is we can do a command called get endpoints. And what this shows us is any matching endpoints for that service. So my app has got one endpoint, and it's this IP address on port 8080. Now, what this IP address is actually the IP address of our pod. So if we do get pod and we can do -o wide, this just gives us more information about the pods. You'll see my pod is running on that IP address. So you'll see the service has one endpoint and it's that IP on that port. So this is how you can start mapping your pods back to a more static service effectively. And yeah, so that's the service. We can do something very similar to what we did with the pod. We can actually port forward to the service. So you can do this by doing svc / then my app, and we want to bind port 80 to our local 8080. Oh, wrong way around. I always get this the wrong way around. There we go. So yes, that's the port on your local machine. That is the port on your service. So I've bound the port of port 80 on that service of my app to my local machine on port 8080. So hopefully, if I go back to localhost 8080, I still get hello there. There we go. So the service is working. So there we go. Now we have a service which can route traffic to our pod through a more static address, if you like, than the ephemeral ones that the pods are given. So while a service is useful as a more static address, it's not commonly used by people. It's more used inside the cluster itself. Where people might interact with a service is where Ingress comes in. And Ingress is a kind of higher level object that sits above a service, which tends to be more concentrated around host names and paths. So for example, an Ingress can have a host name such as example.com that maps to a service, and then that maps to a pod. So an ingress is like almost a relationship between a host name to some kind of backend IPs and ports, which then in turn goes to your pods. Ingress can also be used to split traffic based on different paths, for example. Like you can have something switch on /API go to one service, where /Taris could go to a different service, and therefore different pods behind the scenes. So think of Ingress being a higher level object for determining where traffic should go based on host names and paths, where service is merely just directing traffic to pods that matches selectors. So an ingress is defined, again, in a similar vein to how we've been defining everything else, using some Kubernetes YAML. So again, we have API version. Ingress has a vanilla API version there. It has a kind, which is ingress. It has a name like the rest, and it has a spec. The spec of an ingress is all about kind of hosts and paths and ports. So you have a host, like a host name. You then map to a path. So in this example, it's just going to path /, so we're actually telling it to route all traffic effectively that doesn't, just by default, route all my traffic through here. And it will go to a service name behind the scenes. This maps back to a service and onto a specific port on that service. So I also have a template for this in the repository, so we can do the same thing. I'm going to use myapp.learning.com as my host name. This doesn't really matter. I'll become clear later, but for this example, we use that. Path / backend is service name, and we got to make sure this matches. So I call it my -app. So we got to make sure the service name matches, and service port was 80. So now I have an ingress called, which will listen for any traffic coming onto this host, and any traffic at any path will get forwarded to the service called my app on port 80. So again, same as how we create the service and the pod, we can now create an ingress by doing the same thing. Templates ingress.yaml. Okay. Also, fun warning there, networking v1 beta 1 ingress is deprecated. So that's a good point. This is the new API version that people should be using going forward. Thank you, kubectl, for that handy reminder. So now if we do kubectl get ingress, we'll see we have an ingress called map. And on its host and its ports, and there it is. So that is now a thing that is in our cluster. Now this host name is not like, it's not real. We don't have a DNS registrar or anything, but what we can do is we can do some little magic with Minikube to make this work on our local machine. So if you look in the make file, we have a command called make hosts. And what this is going to do is it's going to echo your Minikube IP with the myapp.learning.com bit into your etc host file on your local machine. And this will effectively just mean that myapp.learning.com gets routed to your Minikube cluster. So that we can test this hostname based routing. You don't have to run this command if you do not want to, but it is in here, so you can do sudo make hosts. And there we go. So we should have something in /etc hosts for that. Yeah. In fact, I have an old entry, so I need to also just edit that out of my host file. Otherwise, that will cause problems. There we go. So now, if I curl myapp.learning.com on port 80, actually just curl myapp.learning.com should work. Okay, hello there. Well, there we go. So I can now hit a host name, and I'm actually hitting the service and then getting transferred through to a pod and getting my hello there back. This should also work in a browser. If I go to myapp.learning.com, I get hello there back. So there we go. So that's an ingress, which is something we can use to direct incoming traffic to the cluster. This is commonly used, for user-based traffic or anything coming external to your Kubernetes cluster tends to come through an ingress because it allows you to associate actual real host names and paths with your underlying services, which are a more Kubernetes concept. Now at this point, we've basically got a web app that is somewhat akin to what a normal web application might actually look like. We've got a host name, we've got a service, and we've got an application backing it all, and we can hit a host name and get a response. However, running things as static pods like we just did is not actually common practice. It's good for learning, but not what you would commonly do, because generally you probably want more than one of your application running for high availability, and you want to be able to do things like updating your app to make it a new version or something like that. So this is where the next concept comes in, and that is known as the replica set. Now, a replica set is responsible for maintaining a number of pods. So it has like a pattern or like a recipe of like, I'm going to create this pod and I'm going to have 4 of it, and it will try and maintain that at all points. So if one of those pods gets deleted, goes away, node shuts down, or whatever, the replica set will create a new one. And that is all it basically does. It just constantly keeps a static number of pods available for you. Now, it's quite rare to use a replica set on its own. Instead, there's like a higher level controller called a deployment object. And a deployment object creates replica sets. So deployment creates replica sets, and those in turn create pods. And what this can be used for is to create multiple versions and rollouts of an application. So when you make an update to a deployment, let's say we change something about the deployment, it will create a new replica set while leaving the old replica set there. Now the new replica set will start to create pods that match the new template. So let's say this is a new version of your application. It will create a pod of your new version while still retaining the old versions of your application. Then once those pods get up and running from the new version, it'll start taking down ones from the old replica set. and start kind of increasing the weight to the new replica set. So 1 by 1, or depending on how you configure it, maybe 2 by 2, or etc. But over time, it will slowly transfer so that all the pods are now under the new replica set, and the old replica set had no pods remaining. However, it does keep it around because this can be used as a rollback strategy. So we can always go back to that old replica set if it turns out something terribly wrong with the new version of our deployment, let's say. So how do we create a deployment? Well, again, it's some more YAML, and this time it's a slightly more complicated looking one, but it's not actually that bad once we break it down. So we have the kind deployment. We have a slightly different API version for this. We have the name again, and then the spec. So there's some interesting things in the spec, one of which is the replicas, so that's how many copies of your application you want running. A selector, which is similar to how the service had to select what pods it was going to manage. This is very similar in that the deployment also has that. So we have a selector where we match labels. We have a template, and then the template bit is all referring to the pods that we're going to start spinning up. Okay, so this is like the template of which it will create 4 of. So again, we can give them a label, similar to how we gave the pod a label. So this bit all mirrors what was in the pod spec. With the app, and then we define our containers, which again is the same as what was in our pod spec. So this part, or the template part, is just a pod, effectively. At this point, we define the template of the pod, and at this high level, we define how many replicas we want for that pod. So if we go back into the templates directory, we'll find there is a deployment.yaml manifest ready for us to fill out. So we can do a few things here, such as giving the deployment a name, stick to the my app, say how many replicas we want, say 3. Make sure we have a selector that matches. Remember going, so the same as what was in the service, for example, select out my app. Make sure that all lines up. We'll carry on the my app here with the labels we give it. And then this can be almost identical to the pod YAML we did. So we can do the server name, and I want to use my app latest as the image. Remember, this bit is effectively just exactly the same as what was in this pod bit here. This is effectively the same. We're just defining the template of what we want our pods to look like. So now we can do the kubectl apply command again, this time on the deployment.yaml, and we'll see a deployment's been created. So now if we do get pods, we'll see we've got loads of pods. So we've got 3 pods have been created, and all of them are our app. You can do the logs, for example, starting up. Now, we can delete the old pod, by the way, at this point, which is probably a good idea. Let's get rid of that. Cool. Nope, sorry, delete pod. My pod, kubectl delete is just a way of getting rid of things. There we go, so my pod is deleted. We're just left with our new deployment-based pods. So if you do kubectl get deployment, you'll see we have the deployment, which is called my app. We've got 3 pods, they're up to date, available. And you can also do kubectl get replica set, and we'll be able to see that replica set that got created as well, which is my app random string. Now you'll notice if we look at the pods, they kind of follow this pattern. So what's happened here is we have a deployment called my app that went and generated a replica set called my app db9 blah blah blah, and then the pods all have this db9 suffix to them, because they're all part of the same replica set, and then they also just have a random string just to make them unique. So those are our 3 pods, all as part of our deployment. Now if we look at our service endpoints again, so remember these were the pods that got matched to our service we created earlier, we should see we have a load now. There we go. So we have multiple service endpoints, because my app can now go to any of these pods because they all match the selectors. Just to remind you, if we do get pods-o-wide, we'll see these IP addresses here match up with these IP addresses here. So if we curl my app learning.com, we should still get a response. And there we go, we get hello there. Now, we can also scale the deployment. So there's a command in kubectl called scale. We can do scale deployment deployment name, so my app, and then how many replicas you want. So if we want 4, we can get 4. Now if we do kubectl get pods, we'll see that we have 4 running pods because a new one has been created at the top there. So cool, now we have multiple pods, all just copies of one another that can all serve traffic independently. Now, what happens if we want to create a new version of our app? What happens if we want to change something? So going back to our actual application, maybe I want to change the message it says here. Like it says, hello there, everyone, for example. So I can create a new Docker image based off this. So if I do make Docker, I'll have a new image with that new message. But all my pods are still the same, right? They're all just my app. And if I do my curl command, I'll still be getting hello there. Now, if I delete one of these pods, the new pod that gets spun up in its place will have the new version of my image and therefore should respond with my new thing. There we go, hello there everyone. But you'll see I only get that some of the time because only one of them's actually got it. Now the reason for this is because we are using in our deployment.yaml the image name called myAppLatest. So this is just whatever the latest version of my app is. And this is generally something you don't want to do, especially in production, because you never really know what you're running when you're running myAppLatest. So what's much more common is to run with some kind of tag, such as v1.0, let's say. That's a tag that we could use. And this way you can start to manage the versions of your application instead of just relying on whatever the latest build of it was. So we can do this, and then we can also create a Docker image with that. So if you use my Docker tag equals v1.0, it should have created a new image, and we can check in Docker images, where it says my app v1.0. Just to reiterate, let's make Docker tag equals v1.0, and you'll get yourself a version of your app with the v1.0 label. So now that we've done that, we can do a kubectl apply out of our new manifest with the new version. Now, with this, it's quite fun to watch what happens. So I'm going to split my panel. Hopefully you can all see this all right. And do a watch kubectl get pods. So over here you can see all the versions of our app running. Now I'm going to do a kubectl apply -f, and you'll see containers are creating and old containers are getting terminated as our new version starts up. Okay, now the last one's gone, and we're down to 3 versions of our app. So it's slowly rolled out a new version, and you'll see we have 3 running. You'll see that the hash has changed. So if we look at our Replicasets again, RS is a shorthand for Replicaset, you'll see a new Replicaset was created 31 seconds ago called my app with this random hash. This was the old one that we originally started off with, and this is the new one with our new version, and all our pods follow that same convention. So if I do my curl command now, all of them will respond with hello there everyone, because they are all on this new version of an app. So by versioning your images with tags, and then by changing the tag in the actual deployment manifest, you can trigger this rollout so that we can gracefully kind of switch over to a new version of an application. Now, the demo we just did there worked all very smoothly, but what happens if I do something wrong? What if I release a version of my application which doesn't work, for example? So what we're going to do here is we're going to purposely break things. And I'm going to just very simply break this in that I'm going to bind my pod to port 8081. So now it's listening on the wrong port. So the service and all the other things aren't going to work anymore because this port is wrong, causing issues. So if I make a new Docker tag, configure 1.1 with my new broken code, and while that's building, I'm going to change this image to my app 1.1. We can do a rollout again. So we're going to create a new deployment, and the new pods will start spinning up. The old ones are terminating. So what's happened now is we've got 3 apps, all of which don't actually work the way we wanted them to. Because if I go and curl, I get 502 bad gateway because there's nothing now can actually respond on port 8080 as I changed it to port 8081. So this wasn't very good, as I've just managed to take down my website, whatever, because I've just deployed a bad version of my app. Now, I use a somewhat, contrived example, but the idea is you could end up rolling out something that causes everything to break. Now, the good news is we can work around this quite easily because Kubernetes has a concept of a readiness probe. So a readiness probe is a probe you define to check whether your app is behaving the way you expect it to be. So there are different types of readiness probe, but for this example, we'll focus on just a HTTP GET, which is perhaps the most commonly used one. And what this will do is it will just check on a given path, on a given port, whether it gets a 200 response. And this is a way to safeguard against you accidentally deploying something that doesn't work. So we can go and define this in our deployment. So it goes in the container spec. We can add a readiness probe, and then we're going to do a HTTP GET. And then we're going to do path. The path, well, for our app can be anything, but a common one might be path/help. And we will do this on port 8080. So now we've defined a readiness probe, and this will be able to determine whether our pod is ready or not. So if we do a new rollout, something slightly different will happen now that we have this readiness probe defined. So we will deploy this on one side. And similar, we will watch the pods again because something slightly different will happen this time. So my new pods have started creating. You can see it's got a slightly different Replicaset name, so that's the new one. But you'll see it's not becoming ready. It's currently 0 out of 1 ready. So the remaining pods all stay. They stay put because it's not going to continue the rollout until these become healthy. Now, if we look at our pods as well, we can see this. We can do a command called describe. Describe is a very useful command which will give you additional metadata about your objects as well as giving any events that might have occurred on them. So if we describe that pod that's bad, we'll see it's unhealthy. We see here, warning, unhealthy, readiness probe failed. So it failed to respond on the port, and therefore this replica set will not be progressing. So we can see the replica set, we can see our old one, which is still at desired free, current free, ready free, and we've got this new one I just deployed, which has failed because the readiness probes have not worked. So it's just blocked it at this point. Now, if we go back and change this to version 1.0, which we know works, and now do a rollout, this should start passing. So what we can do now is again apply our new manifest, which has been reverted to an older version of the app, which we know works. we should see new pods starting to spin up again. And they wait a little while because they need to make sure they pass their readiness probe. But there you go, it passes, and then the old ones start to terminate. So there we go. This time everything's good, and we're left with some apps that should be working. So again, if I curl myapp.learning.com now, I'm back to getting my response because all of these are healthy and they've passed their readiness check. So defining a good readiness probe on your application is very important. This will ensure that your rollouts actually succeed and that your new versions of your apps are working as you'd expect. So not only does it not progress the rollout, the actual service will not send any traffic to pods that are failing their readiness. It's also worth noting that readiness can fail during a pod's lifetime. It constantly checks this. This isn't just at start, it's also throughout its lifetime. So if your app breaks for any reason during its running, while that readiness probe fails, the service will not forward any traffic to it. So users should not see that that pod has failed. And then if it recovers and starts passing its readiness probe again, then it will start receiving traffic as per normal. Also, as a side note here, there is actually a different type of probe, which is very similar, called the liveness probe. The liveness probe takes the same kind of arguments as a readiness probe, but it has a slightly different role in that the liveness probe will actually kill your container if you fail it after 3 times, let's say. It will just kill your container, causing it to restart. These can sometimes be confused and used interchangeably, but they have quite different purposes. A readiness probe is all about determining that my app is healthy, deployment can continue, I am ready to serve traffic, etc. A liveness probe should only be used in certain scenarios, such as when your app is somewhat prone to getting itself stuck in a state where it needs a full-on restart to recover. That's where a liveness probe should be used. They're often used interchangeably, but that's often for a wrong reason. Like sometimes you don't want to restart your app if it's failing its readiness. Maybe it's failing its readiness because it's struggling to talk to another service, which is having some kind of network problems, but that will soon recover. So there's no actual need to restart my app. I should just wait until I'm now ready, and then I can start doing it again. And sometimes causing things to get restarted because they fail can cause all sorts of cascading failures. So be careful about using liveness probes. This is my tip there. Always use a readiness probe. Liveness probe, use it if you need it, but if you don't worry about it. Now at this point, we have a relatively well-formed application being deployed to Kubernetes. We have readiness checks to make sure it's ready. We have multiple replicas of it for availability. We have a service sitting in front of it to route traffic to each of our pods. And we have Ingress to allow host names to be mapped to our services and pods. So this is looking somewhat close to what you might actually deploy in a real-life production cluster. But for some additional fun, let's say, I thought it'd be interesting to look at doing some runtime kind of configuration of our app. Now, going back to our application, you may have noticed that it actually reads something in at the very start from a file. It does a read file on a file called stuff.txt, which is in /etc assets. Now, this is loaded into a variable and is part of the response where we say, hello there, everyone. We also reply with this. However, currently there is nothing there. So that's why we're getting nothing back. So if we want, we can insert something into this directory and that will get printed out. So a common way to do this in Kubernetes is using a config map. A config map is a resource that can be used to store config. It is of kind config map. It has a name and it has data. And in this data, you can create files effectively, such as stuff.txt, and then put whatever content you want in this file. Now, for this example, I've decided to put a little bit of ASCII art of a rabbit holding a pizza sign. However, you can put whatever you like in this. This can be a configuration file, it can be just some strings, some CSVs, some JSON file, whatever you like can be stored in this config map and used by other things later. So we can go and create a config map. I have a template in a template folder. So we can create one called my config map, and we'll create that file of stuff.txt. Now I'm going to just copy that little ASCII rabbit from my example config map over here. However, you are welcome to either use this, or if you want, you can create your own bit of ASCII art, or whatever your heart desires. This is completely arbitrary. Anyway, there we go. So we have a config map created, and it's got a text file which just has some ASCII art in it. So we can now do the kubectl apply command. And our config map has been created. So similar thing, get config maps, show us our config maps, and we can see I have my config map. If you want to look what's inside this, you can do a get config map, and then the name of your config map, followed by -o space YAML, and this will output what's inside the config map. So there you can see the stuff.t. There's our little pizza rabbit. It's right there. So there we go, we have a config map. So this is just stored in the cluster at the moment. This is just a resource in the cluster. So the next step is to actually put this into our pods. Now, what comes into play here is volumes. Now, volumes can be attached to pods, and then any container in that pod can read from a volume. A config map, for example, can be used as a volume in a pod. So the containers in the pod will access the volume, and that will be populated by the contents of a config map. So worth noting that this config map can be shared between many volumes in many pods. So one config map can populate a volume in multiple different pods so that they can all have the content that's contained in this config map. Now, the way we do this is with two things that we're going to add to the deployment. One is the concept of a volume, and the other is a volume mount. Now, what a volume is it's just a definition at the pod level of what volumes I want accessible in my pod. So in this example, we have our assets, that's just the arbitrary name, and then saying I want this volume to be from this config map, called my config map. And then you also have something called a volume mount. And the volume mount is when you mount this volume into your actual container. Because remember, you can have multiple containers in a pod, so you might want to mount the volume into different paths in different containers. So volumes is at the pod level, volume mounts is at the container level. The individual containers in a pod can mount the volume into a different place if they so desire. So we refer to the name we defined there. We're going to mount this volume into our container, and we'll say what path we want it to be mounted in. So we're going to go back to our deployment YAML, and we're going to define these things. So first, we're going to define the volumes. Now, the volumes, are at the same level as containers because they're a pod level thing. They're accessible by all containers in the pod. So I'm going to create a volume, give it a name, arbitrary. We're going to say it's a config map, N. And the name of that config map was my config map. There we go. Now inside the container, we're going to create a volume mount. And this name here is matching this name here, so we're mounting in the assets volume, and I'm going to mount it to /etc assets, as that is what matches our server here. It's expecting something in etc assets called stuff.txt. There we go. We've created our volumes and we've mounted the volume into our container, the server container. Now if we do a new apply, there we go, got a new rollout, so we should see new pods starting to come up as we expect. Yeah, they're all coming up successfully. The old ones are starting to terminate. Good. So now, if we call myapp.learning.com, we get hello there everyone and the pizza rabbit. So there we go. It's loaded in that config map, and it can now output that. So that's how you can use a config map to inject runtime configuration into your application. Now, to finish off this presentation, I thought it might be fun just to share some useful kubectl commands with you all. There's many different kubectl commands, but there's a few that everyone should be aware of and will make your life a lot easier as you start to do things with Kubernetes. These are things I'm regularly telling people to do or telling them about because they tend to answer a lot of questions or solve common problems when trying to debug things in a Kubernetes cluster. So we'll start off with kubectl describe. So we used this a few times in the course of the workshop, and what this will do is it will give you a lot of information about the object you're describing, but also it gives events, and events are super useful because events tell you things that are happening to your pod. For example, if your pod is failing its liveness probe or its readiness probe, this all gets told to you in events, and generally useful things will be given to you in this events section, which will give you indication of what's going wrong. Just to remind you, kubectl, like get pods, you can do kubectl describe pod, and then on your pods, and you'll get a load of different information about the pod, but also these events down here. These are all just happy events here, such as it scheduled the pod, found the image, and it created and started the container. But will also give you often quite useful error messages down there if something's gone wrong. You also will see this kind of information in the kubectl describe, which tells you about the current state of the container, such as its ID, its image, any ports, the argument you started it with, and the state it's in. Such as, for example, this one is in a crash loop backoff, which means it's kept restarting over and over again. So it's on a hold at the moment because it keeps restarting. See, this one restarted 407 times, so it's not in a happy state. Again, if we go back to my terminal, you can see all this stuff, information here, where this container ID state is running though. Everything is happy on this one. But this will often give you ideas to why something's restarting. It will tell you why it's restarted, things like that. These are all found in kubectl describe. So I recommend describe objects if something is going wrong. It will often give you some of the information you need to further debug. Kubectl logs we already used when looking at pods, and again this is just very useful for doing some little bits of debugging. If you need to find out what your containers are outputting, you can use the kubectl logs command and it will give that. You can even follow the logs and have like a live stream of them if you so desire. Generally, if you are running Kubernetes clusters at scale, though, it's a good idea to have a proper centralized logging system so that all these logs get scooped up and put in a log index somewhere so that you can query them at a later date. Because remember, pods do not last forever. They are intended to come and go, and you will lose all those logs if they go, if you do not have some kind of backup system to centralize these logs. This can be useful in some debugging scenarios. Port forward was something we used a few times and is very good at debugging why your networking isn't working. Let's say your Ingress doesn't work or your service doesn't work. Using the port forward command to actually connect to a pod and test the ports on your local machine just to kind of sanity check that the pods are listening on the port you expect they are, or the service is listening on the port you expect it to be, can often be very helpful when trying to work out, well, why isn't my service working? Why does my Ingress respond with 502? Or something like that. It's a good way of just going, okay, well, let's try this out and see what results I get. Yeah, and you can see here you can just curl from your local machine as if you were directly attaching to the pod. So yeah, that's a very useful one, and well, not everyone necessarily knows about. So I thought I would just call it out as it's good for when you have those awkward networking issues. Yeah, you can also port forward to a service by using the service / command and then the name of your service and the port. instead of a pod. So by default, if you just put a name here, it will assume it's a pod. But if you put SPC, it will know it's a service. And when you port forward to a service, you get load balance between the pods, like if you were to hit the service, which can be good to sometimes check. I don't know, maybe one of the pods is behaving strangely or something. You could use this to debug that theory. And that brings us to the end of this workshop. I hope you have learned some things about Kubernetes and containers and pods and all this wonderful world. There's plenty of other resources online. If you are interested in knowing more about this topic, please do have a look. But I hope this at least gave you a chance to play around with some of the fundamentals. You can always try extending this stuff, changing the Go application that's in the repo, and see what other things you can do in this repository itself. But yeah, I hope this was of some use to everyone, and I hope you enjoy the rest of the conference. Thank you very much.